Welcome everybody. My name is Neil Davies and
my name is Brad Monaghan.
So today we're going to do the next in our series of PD webinars, and this one, currently only started.
We're going to start.
Okay. Good morning. Welcome everybody. My name is Neil Davies.
And my name is Brad Monaghan.
So today we've got the latest in the series of the webinars on PD, and we're going to talk about failure prevention through effective cable monitoring. So PD on cables and monitoring today. As we go through it, we're going to be presenting a lot of slides. I'll start that off and then hand that over to Brad for case studies. If you have any questions at any time, there is a question box, so please feel free to put them in there. We will take them. We will try and answer them either verbally or text as we go through. And at the end of the session, we've got a question session as well. We'll also be monitoring the chat area as well. So if there's any issues, any problems, then please just flag those up and we'll deal with them hopefully as we can. Okay. So let's move on. Okay, so the contents today is we're going to very briefly cover why we're testing for PD on cables, so and ask the why question. We'll very briefly also look at the causes of cable failures. Small section on cable terminations, but it's not where we're going to concentrate today. We're going to really concentrate on looking down the cable, how we can find discharge that's happening on the joints and the cable down the length of the cable. We'll talk about the different technical considerations that you should have when you're looking at monitoring and how you're going to monitor. Brad will then cover in a couple of significant case studies, and we'll summarize that, and like I say, questions at the end. So questions whenever if you feel you need to put a question, write that in at any time, and we will mop up anything that we don't answer at the end of the presentation. So let's start with the why. Why are we monitoring for cables? Now HV underground cables, they're aging assets. We've got lots of large networks. There's different types in there. We've got old paper lead cable. We've got early generation XLPE. We've got new cables. So there's different types, different quality of assets that we're getting in there. And typically for underground cables, we have limited condition data. So they're almost a bury and forget, if you like. We can see our switchgear, we can see our transformers, we can see if things are deteriorating from a physical perspective. But in cables, we generally don't get that luxury. We also know that failures in cables cause significant impact. So they have a real big material impact on the network performance. On whether it's an industrial site or whether it's a distribution network operating site. If you get a cable failure, it can really cause you a lot of money in terms of outages. And typically when we look at any condition monitoring in the high voltage assets, there's three main focuses that we look on. We're always looking to increase safety. So we don't want things to blow up. We certainly don't want people to be injured. When we're looking at cable terminations, that's more of a safety aspect. So you can see in this particular picture here, we've got the cable box on the right hand side of the picture is blown up. If you're in the substation at that point, that's going to be a significant safety concern. When we're looking at underground buried cables, then obviously at times the direct buried cables, you're going to get a bit less on the safety aspect. But when this cable joint in the middle here blew up, one thing that you can be certain for an unplanned failure is you're going to get significant outage, and that's going to cause you problems, which can also be safety problems. So if we can prevent this sort of thing happening or be proactive in taking these defects off the system, we're going to improve our safety, we're going to get improved asset performance. And if we do those two things, we're significantly going to get financial benefit. So there's a cost, safety, and an asset performance benefit in preventing these failures. When we actually look at what causes failures, we did, in EA Technology is in a good situation where we do a lot of forensic investigation of HV faults. And we looked at the database of the failures that we've been getting in HV, MV, HV, depending on your terminology, cables over the years. And what you can see is that around 2/3 of all failures are associated with workmanship. So unfortunately, when people get involved, whether that's the termination, making the joints, how they're made, it's not the easiest job. You need very well skilled and highly trained people. That may not always be the case. And so what we find,
I've just got one thing,
Yep.
sorry. So someone's got Adrian has got we've disabled connecting to the webinar by phone. It's one of the settings. Sorry, just a technical issue.
technical issue?
Yeah, Adrian's trying to connect to the webinar by phone, and we must have a setting.
Okay, options.
Yeah, we will send out the video of this webinar to you, Adrian. Not possible to hear from phone.
I have no idea.
Yeah, I have no idea either how to change that setting.
There's nothing that we've clicked.
No. Preferences.
Okay.
No. No, let's not that one.
No, there's nothing that we can.
Sorry, Adrian. We'll get the picture of the video to you later. A link of the recording later. Apologies.
We'll look into that. So yeah, let's go back to what causes HV faults. So workmanship, unfortunately, is a significant factor. So when you're looking at that workmanship, then the early life failures are going to be a thing to consider. So this isn't just technology that you should be doing on the aging assets. It's really for that beginning of life asset as well. And manufacturing defects are not insignificant. There's 16% of that. So of course, the whole asset management approach is buy good quality stuff, get it put in well, manage it through its asset life, and then dispose of it well. So that whole asset life approach is significant here. So the manufacturing defects, buy the right things, make sure your jointers and your installers are well trained is a big factor, really. The external damage was actually a relatively minor in terms, so the JCB or whatever digging into a cable is not as big thing. Now, age-related failures in the database that we've got here are also relatively small, but that is set to increase, or is likely to increase as our networks get older. So this is why it becomes really important, and why people are really focusing on the underground cables nowadays, is that these assets are aging, and the bathtub curve is not a lie. You will ultimately get to a stage where the insulation starts breaking down and the asset gets towards end of life. So failures tend to then increase. Now, PD, partial discharge, is the biggest indicator. So if somebody gets a joint wrong, or the cable papers are drying out and things like that, what will tend to happen is partial discharge will occur. So we'll get the partial breakdown of the insulation in the cable before the failure occurs. So that's the key indicator of the condition for cables. Now that will affect both the different types of cable. So the top picture is treeing that we can see on a paper cable, and the bottom picture is on an XLP cable. Now for XLP cable itself, XLP is very intolerant to partial discharge. So typically when we're looking for monitoring or assessing the XLPE circuits, we're really looking at the joints and the terminations at that point. If we get discharge happening in the bulk of the XLPE, it tends to accelerate to failure very, very quickly. we tend not to get that PD, long-term PD, whereas in paper cables, you will get discharge occurring in the bulk of the cable as well as the terminations. So for XLP cables, it's typically the joints that we're monitoring and we're looking for the problems. Whatever happens, once you got partial discharge, it will start eroding the insulation and eventually lead to complete failure. Okay, one brief mention of the cable terminations. The whole cable termination thing, is it actually the switchgear? Is it a cable problem or is it a plant problem? If you talk to the cable engineers, then it's the switchgear responsibility, and the plant engineers will tell you it's a cable issue. And nobody wants to take ownership. This is where we get a lot of failures. Now, in order to test cable terminations, you don't need the handheld type equipment that we've talked about many times, which is the UltraTev type equipment where we're testing for ultrasonic, we're testing for transient earth voltage signals, are perfectly adequate for finding cable termination issues. So the top picture is a classic cross phases, poorly installed dry termination. This will be roaring away ultrasonically, so we will be able to find that using ultrasonic techniques. And we can pinpoint exactly that it's coming from the termination because of that ultrasonic activity. The bottom picture is one where it was a plug-in type termination and manufacturing defects. So again, a joint defects in here. This was picked up using transient earth voltage, and the cable terminations were isolated, stripped down, and found to be a problem. So just measuring on the outside of that using the TV technique, we'll find those sorts of problems. So using that handheld is a perfectly good way of finding termination issues. What we're going to, or using even the monitoring, using the TEV and the ultrasonic technique is a good way of finding it, whether it's monitoring or handheld. What we're going to talk about more now is looking down the cable at cable PD. So finding the cable PD that isn't associated with the terminations, or of course the associated plant, maybe the bushings or the switchgear transformer. Okay, so when we get partial discharge happening in cable, then we get a high frequency pulses are generated that travel along the conductor and in the opposite polarity along the sheath of the cable. So let's say we get PD happening in this location here. The signals will be generated, like I say, they'll travel along the ground, they'll also travel up the conductor in the opposite polarity. They will travel in both directions until it sees the end of the cable and the change of impedance, and the signals will then bounce back. So if we're measuring at one end, whether we're doing this online testing through coupling capacitors and VLF type testing or oscillating wave testing, then we're measuring at one end, we will first of all see the pulse that comes directly from the discharge site at the sensor. The next pulse we see, the second pulse along, is the indirect pulse is going to be the one that starts at the discharge site, bounces to the far end, and then comes back down to our sensing point. And the third pulse we see, if we can see that one, is a reflection. So the first pulse going all the way back and then coming back to the end of the cable. So if we can see those three pulses, then that allows us to do quite a few things. That allows us to measure the amplitude and locate the cable. Now, obviously, when we've got signals traveling up these cable conductors, then we've not got a perfect transmission medium, so we will get losses occurring. So the propagation, the signals, the classic signals as we see at the top here, will look more like something at the bottom by the time it's come down the cable on a long length of cable. Now, how much those signals attenuate, affected by different things. So the type of cable, so they will attenuate less on XLP than they will on paper cable. The length of the cable, the further it's got to travel, the more the high frequency component will be lost. Loading conditions can play a part when it's online testing, so how much noise you can see. And the the propagation characteristics of that cable. All of these things affect sensitivity of the PD, of locating the PD source within cable insulation, whether you're looking at online or offline techniques. So that high frequency component will disappear. We'll talk about frequency, and applying filters as we go in the next few slides. But if we get all three of those pulses, that allows us to, one, give us the magnitude of the discharge. So we measure the first pulse, and the area under the curve of that gives us a magnitude, generally measured in picocoulombs. And then if we can see the distance, we know that the distance between pulse A and pulse C gives us the length of the cable, and the distance between A and B gives us the location of the PD signal with respect to the full length of that cable. So if we can measure all three of these pulses, then we can give you the amplitude of the discharge and also the location of the discharge. Okay. So let's talk about, we're going to talk more now about using monitoring and using monitoring towards asset management or effective asset management, and how that plays a part, and the things that you need to consider when you're looking at monitoring cables. So in this particular instance here, we've got in the picture here is a dedicated cable PD node. It uses high frequency current transformers that plug into the node just to look and concentrate on monitoring cables. It plugs into our standard switchgear and cable monitoring system, the Astute monitor that we've got in the picture there. So you can have a combination of the standard TEV ultrasonic, which we use for monitoring switchgear, and link into that chain these dedicated cable nodes that we've got here for monitoring cables. If you're wanting to monitor air insulated switchgear and you want to monitor the cables and switchgear themselves, then we do always recommend, and we do always put in these two different types of node, so that you have the transient earth voltage, the ultrasonic measurement for the air insulated switchgear in particular, and the terminations, and the HFCT measurement for looking down the cable. If you're looking for monitoring medium voltage GIS type switchgear, so say 33 kV GIS switchgear, you can actually just use that one HFCT sensor for monitoring up towards the switchgear and also down the cable. Now, the trick with doing that is selecting the optimum frequencies on filtering. If you put quite an aggressive high pass filter in there, say a 5 megahertz high pass filter in, then you would be concentrating on looking up towards the switchgear and looking for PD signals in the switchgear itself rather than far down the cable. And we're going to talk about the filters there. So if you're looking for monitoring further down the cables, then you need to choose the filter a bit more carefully to give you the right distance to look down cables. So for monitoring and also for handheld, the factors that you have to consider we're going to talk through now. Now, first thing is you need access to the cable sheath in order to put the HFCT sensor on. Now, when we're looking at a picture that we've got here, this is some 33 kV GIS switchgear, and typically on that with the plug-in type terminations, you will get really good access to the earth screens. They're outside, they're not inside the switchgear, not inside a cable box. We plug in the HFCT. We have these 50 millimeter or 100 millimeter sensors here. We've actually put a lot of effort into making improving these HFCTs in real time and getting very high sensitivity to cope with noise and things. So the HFCT goes around the earth screen in this location. So we've got one here on each individual phase, and it has to be in the situation where you have, if you've got a 3-core cable, we need an insulated lug. So we've just measuring in the signals on the earth, just the earth itself. On the plug-in type terminations, again, it's nice and easy for that. A lot of switchgear nowadays, you will have the situation where you you don't get access to the cable. You don't see that, and the screens are terminated inside the switchgear. If that's the case, then the only true way of utilizing this technology is to maybe permanently install HFCTs inside that switchgear, take out the cables, run them up the channel through maybe to the secondary chamber into a breakout box. And that allows you then to either temporarily monitor or temporarily test the cable. So access to the HFCT or access to your screen is absolutely paramount in order to do this test. If we were to place a conductor, the HFCT around the cable itself, where we're going around the earth and the conductor, then all we're actually going to do is we're going to get the two signals, the one coming up the conductor and down the earth, which cancel each other out, and we're not going to be able to measure anything. Okay, so that's the first factor, is whether we got access to that earth in order to do the testing. The next factor that we have to do, and it's very important, is to figure out the level of noise that we get on circuits. Now, this can vary greatly. It can be much more of a problem on industrial networks as compared to distribution networks. But that's not always 100% either. So in this particular case here, this is an industrial network, and this is a series of data which is showing you unfiltered data. So very, very high levels of noise right way across the 360 degrees of the sine wave. Lots of generally lower frequency pulses are being measured in this particular data. So that's the sort of situation where you'd be struggling to find PD within these signals. And the first thing that we do is start applying filters to take out some of this lower frequency noise. So the first filter that we apply in this particular case is a 500 kilohertz high pass filter. So it still allows you to look quite far down, or very far down the cable, but it's taking out some of that noise. And you can see we've taken out a good proportion of the noise. However, we're still getting relatively low frequency signals coming through, and you may have to go through a lot of these waveforms one by one to see if you're getting any indication of PD. So it can be more aggressive, and the next filter that we put on in this particular circuit was a 1.8 megahertz high pass filter. And immediately as you put that 1.8 megahertz high pass in there, this is an XLPE cable, it's about 2 kilometers in length, then we can see the clustering appearing, which gives us an indication that we're seeing phase resolved partial discharge, and we're getting these high frequency pulses that are seen. So in this particular instance, we've got a 2 kilometer long XLPE cable. The PD has been located to around 700 or so meters, so using a 1.8 megahertz filter. So we're still, even with a relatively aggressive 1.8 megahertz filter, able to look at decent length on this XLPE cable of 2 kilometers. We can see at the far end how much the final reflected pulse is almost lost in the noise, and any more filtering on that and we're going to lose that pulse. Any more noise, we're going to lose that pulse. So I've got another 3 examples here of the effects of filters before I hand over to Brad and the case studies. This particular one is on a hybrid. It's XLPE tails into a paper lead cable, so an older circuit, and this is 1.4 kilometers long. And this instance, it's very quiet. We've got very limited in the way of external noise or noise on that system. So we're finding the discharge here roughly about 55% up the cable on the 1.4 kilometer long cable. You can see the first pulse coming to us, the first reflection, and then the far end of the cable. Perfectly able to see both the clustering and the unipolar PD pulses and locate that conclusively to about 55% of the length of the cable, and with a discharge level of around 2,500 picojoules. If we were to apply that 500 kilohertz high pass filter, you can see again we can still see quite conclusively the 3 peaks, and locate the discharge, and we can still see the clustering. And applying the 1.8 kilohertz filter, we can see the reflected pulse, we can see the first pulse, we can see the clustering. We're starting to struggle to see that final pulse, which confirms the length of the cable. But in this particular instance, we can just about see it. So for a paper-led cable, 1.4 kilometer, relatively clean, we're just starting to hit the sort of limits. This was using a CT, an older CT, so nowadays we can see quite a bit further than that with the best CTs that we have nowadays, but that's still looking at the sort of lengths that you're starting to hit with paper-led cables. So the less filtering you can put on, the better. So if we've got a clean cable, unfiltered allows us to see further than putting any filters on there. If we put a 5 megahertz filter, try and look into the switchgear, then we're going to severely limit how far we look down the switchgear, look down the cable circuit. We're still going to be able to see 100 or so meters, even with a 5 megahertz filter, but after that, you're really starting to struggle. Okay. Now I'm going to hand over to Brad to talk about the case studies.
All right, thanks, Neil. Thank you very much, Neil. So we've got 2 case studies here. So case study number 1, the joint replacement. Are you just clicking? There we go. Yeah. All right, so here we've got some 33 kV cables. So it's 2 sets of 33 kV cables that are about 4 kilometers in length. These are relatively new in terms of cable assets. They're only 5 years old. And within that 5 years, this customer or this industrial site had suffered 2 previous joint failures. The cables are highly critical to the plant because they're the only feed to the plant. So if any of these 2 cables go off, the plant is off. Okay, so EA Technology was asked to come and try and diagnose whether there was still PD on the cables, and we ran a series of tests. So we're going to go through those tests now. So the first test that we ran was a cable data collector test, and that's where we get our high frequency current transformers. We put them around the sheaths of the cables at the ends, and we run an online test. So we get our computer, we get our cable data collector, we run some software, and we run a capture on all the phases. We do this without turning the cable off, so there's no shutdown. We do it while it's in service. It can be done at any time, as long as we have access to the screens of the cables, as Neil mentioned earlier. So the outcomes of that test was on circuit A, we found PD at approximately 40% of the cable's length, and that can be seen on the left-hand side here. So we see clustering PD clusters along the sine wave, 180 degrees apart. When we look at the waveforms, we're able to see the initial pulse, as Neil was mentioning earlier. The pulse reflected back from the PD source along the cable at about 40% of the cable's length, and the far end reflection of the cable's length. So we're getting good data coming back through here, and I believe that the 500 kilohertz high pass filter was applied to this. So we did apply some filtering to be able to see it. On circuit B, we ran the exact same test. We can see 2 clusters of activity, 180 degrees apart. Quite high level there. That's getting up to about 20,000 picocoulombs on with those filters applied. We can see the initial pulse, PD pulse, far end pulse, and that was telling us that about 20% of the cable's length we could see PD. So that the 40% and the 20% along those circuits lined up with known cable joint locations. So that was very much likely there's workmanship defects inside those joints. Next slide. So then what we did was we did some offline VLF testing. So we advised the customer, let's shut down the cable and run some VLF tests to figure out if there's actually PD at those sites, which we're already confident there were, but we did it to confirm it. So we took the cables offline and ran VLF tests. So on cable A, we found again, at about 40% of the cable's length, we found high level discharge. We found some lower level discharge down here. And then on cable B, at about 20% of the cable's length, we saw PD as well. So we can see the phase plots, we can see the waveforms, and we could see the distances to the PD via the VLF tests. So when you do the VLF tests, you are very much controlling the volts yourself. You can figure out when PD occurs, what voltage it occurs at, what level it gets to in terms of its picocoulomb level, and you can see all of that data within those tests. But you need to do a shutdown to do those tests. And then the third thing that we did was we put on a 24/7 monitor. So similar to the one that Neil was showing earlier, where we put HFCTs, put them into our monitor, and we monitored 24/7 to see what PD activity was doing and how it was behaving. And so we could track it over time while a decision was being made about what to do. So we could see that PD was there over time. We could see the phase plot again. We've got two clusters of activity, 180 degrees apart, similar levels again, about 20,000 picocoulombs, and we could see the waveforms and get a distance to that PD, which all of this was lining up with, there's PD in the joints and it's at these locations. What then occurred was the customer took a planned shutdown and they replaced the two joints that were discharging, one on cable A and one on cable B. So when they replaced the joints, this is where the joint replacement took place, and then they switched the cables back in. And then from then on, around about here was where the cables would switch back on. And from there, we continually monitored again. We still get a picocoulomb level, but we can tell by looking at the phase plot that we are picking up a lot of machine noise. When we look at the phase plot and we see these lines, these vertical lines that go up, down across your sine wave, that's very typical of machines spinning and turning and doing their thing and chopping up the sine wave and imposing noise back through the circuits. We can still see that there is a little bit of PD. You see this cluster here and this cluster here. You can see that that is still evident on the cables, but it's at far lower levels than what we used to have. So if I go back to one slide, this here was the phase plot before the joints were replaced, and we had a level of about 10,000 PC measured on our monitor, okay, and we could get a distance. They replaced the joints, and then all we see is machine noise and low-level PD. So that confirms that the replacement works of those joints was effective. So that's our first case study. And this is our second case study. So case study number 2. So this is a place called INEOS, a company called INEOS. It's the largest petrochemical plant in the UK, and it's also, because of the size of it, it's one of the largest private networks in the whole of UK and Europe. It's critical to, to the running of the UK in terms of petrol and all that type of stuff. And a lot of the oil that gets pumped out of the North Sea comes to here for processing and turning into all the fuels that get used. Now, this place is fed by 18 33 kV single core cables from a power station, and those cables are critical. So on those cables, in the past, they'd experienced a couple of failures, and the company INEOS approached EA Technology to come and install some monitoring and figure out what's going on. They wanted early warning of PD occurring in these cables because they can't afford a shutdown. They want to know what's going on, and they want to, if works need to be done, they've only got basically shutdowns, periodic shutdowns that probably happen every 12 months. I'm not really sure. But this case study covers the time between two of those shutdowns. So what occurred, these cables are 1 kilometre long, and there's 2 joints along each cable run. So they're sort of, I'm not sure if they're a third of the way down or something like that. Oh, sorry, if I go back a slide, so what was installed was a cable monitor. So these here are current transformers that you put on the screens of the cables, and these are the cables themselves coming into the plant from the power station. At the other end of the cable, at the power station, our 18 cables come up and they terminate onto this overhead bus here. all 33 kV. So no monitoring was installed at this end. It was all installed at the INEOS end. So once the monitor was installed back here, 10 days later, we had PD jump up on the cable that's designated as red 2. So red 2 cable, after 10 days, started discharging. Started at about 100 picocoulombs and then rose to about 300 picocoulombs. What we could do with the software was also look for a distance to fault, and we could figure out that a certain percentage down the cable, I think this is about 30% down the cable, we could see PD that lined up with one of the joints that's there. What also happened, if I just go back a slide, what also happened was 2 other phases started to discharge. So you had the red cable number 2, the blue cable number 3, and yellow cable number 1. A couple of days after this one started to discharge, they started to discharge. So we knew that there were 3 cables out of the 18 that were discharging. So now that we've got 3 out of the 18 discharging, you know, what do we do about it? It's critical plant, and these are critical cables that feed that plant. So the main aims is you want to avoid catastrophic failure of any of those joints, and you want to, you know, prevent unplanned outages. You also want to prevent outages for further tests. So another option is to come in and conduct VLF testing, where you take the cables offline and you liven up the cables yourselves to confirm where the PD is occurring. But that is a shutdown, and that costs money and that costs time. Also, they wanted to avoid the cost of outages for joint replacements, and they wanted to, of course, avoid personal injury from any failures that may occur. So what did the company do about it? What they did, they worked with us and the monitoring that we'd installed. So we were able to remotely analyse the data, the PD data, and see how it was performing over time. They had planned a shutdown for 10 months into the future once they already knew that there was PD on these cables. But we monitored them for the 10 months, and we, you know, reported to them about what was going on. So you can see here in this trace that this green line here is the blue 3 cable. The orange line is the yellow 1 cable, and the dark blue line is the red 2 cable. You can see here, this is when their first shutdown took place for us to install the monitor. So this was permanently installed monitoring inside the switchboard. They energized the cable here. 10 days later, the PD kicked off on blue 3. A couple of days later, it kicked off on the other 2 phases. And what we're able to do is track it over time, and we found that it all settled down, but was still very much discharging all the way through until they took a shutdown at this point in time here. They replaced those 3 joints, they re-energized the cables, and we can see from that point on, once they'd re-energized the cables, there were very, very, very low levels of PD, which is basically background noise, which means no PD. So they were able to manage the shutdown, or basically nurse those discharging joints through the shutdown to replace things in a planned manner. And they were able to accept the levels of discharge and accept the risks of the network because they planned for the outage. They got themselves ready with the appropriate joints. They had the people that were going to do the joints, you know, ready and informed that, you know, one day we may ring you because these cables may fail. And I believe they also fenced off the areas where those joints were located to prevent access. So that's how they were able to manage that, which is a really good outcome. Okay, when those joints were cut out of the ground and replaced, they were sent to EA Technologies Forensics Lab in the UK for forensic analysis, where they strip it down and look at everything with a fine-tooth comb to figure out the source of PD. So this is a high-level summary of the joints that were cut out. So you'll see here that there are actually 4 joints that were cut out. There was one on red 2. There were 2 joints on the blue 3 cable, and then there was one on the yellow 1 cable. Okay. What you'll find that all 4 of them had evidence of PD. workmanship was an issue with the joints, and that was the cause of the PD, because here we've got correct application of the yellow stress control mastic. None of the 4 joints had the correct application of that stress control. The correct depth of the XLPE where the semicon cut into the XLPE was made. There were a couple of yeses and a fair few no's. So where we've got a no, that means that the stripping wasn't done to the correct depth. Also the abrasion on the cable outer oversheath, which where the big outer heat shrink, where you abrade the cable underneath it with a rasp or a file to get good adhesion between the two, that had poor abrasion. And then 3 out of the 4 had evidence of moisture ingress into the lead sheaths and into the outer heat shrinks. So workmanship defects had caused these PD sites to occur. And here are the physical joints during the strip down. So this is the red 2 south cable joint, and this is the other one next to it. So here we have evidence of PD, evidence of heat occurring at this location here and at this location here when that red heat shrink there was stripped off. There was evidence of moisture ingress, corrosion, and a lack of abrasion on the red outer sheath. So the lack of abrasion that we're talking about is here, where it hasn't been roughed up with a rasp to get good abrasion. And here there's evidence of moisture coming through where moisture just should not be. Here is where the yellow mastic hadn't been applied properly. Now, if we look on the right-hand side here, this is the yellow mastic that we're talking about, that is the stress control mastic. Here is the lug, and here is the XLPE cut. And underneath there, you can actually see the core of the cable. Now, the problem here was this lug should be, I don't know, 5 millimeters to the right, where you allow a bigger gap for the yellow heat shrink to go into that gap and create a good, you know, for the mastic to go in, so that you get rid of the gap and get rid of all the sharp points. But because the gap was too small, the yellow mastic couldn't go in, and that was causing sparks to jump across this gap. That was also creating, the sparks were creating heat, and that was heating up these heat shrinks, the red and the black heat shrink, which you can see on the left-hand side here. Okay, so that were the outcomes of that exercise, which was a good outcome for the client. They avoided failure, and they nursed it through to the next shutdown, and they found reasons for their problems. Okay, so in summary, workmanship accounts for around 2/3 of cable faults. There was a few examples of that in here, where you've got the incorrect use of tools, the incorrect depths, the incorrect you know, lengths of cuts, and all that type of thing. So that is a big issue, 2/3 of the issues. So when you're testing for cable termination PD, you can use your TEV and ultrasonic techniques locally. We usually do that when we test a switchboard anyway. We'll go to cable boxes and we'll try and figure out if there's any PD within the cable boxes themselves, and the TEV and ultrasonic techniques are sufficient for that. Now, when we're testing the cables themselves, we need to use HFCTs onto the earth screens to test for signals that are bouncing up and down the cables effectively. So the access to those screens is will let you know whether you can use the HFCTs or not. You can permanently install the HFCTs inside the switchboards and bring cables from there out to breakout boxes, or if the construction allows it, you can just do it on the outside of the switchgear, so there's no need for a shutdown to install them. Your system noise needs consideration. So if you can figure out how much noise is on your network on those particular cables that you're trying to monitor or test, you will be able to figure out what type of filters you need to apply and give you a better idea of you know, whether you need to limit that noise somehow or test during a quiet period, because your plant might fire up during the day and it shuts down at night. So maybe you need to do some nighttime tests to see through the noise or limit the noise. And it's always a balance between filtering noise versus length. Basically, if you've got very, very, very low noise, you don't have to apply that high level of filter to see far down your cable. But if you've got very high noise, you will apply very high filters and you can see a less distance down your cable. So one of the big questions is always, how far can we see down the cable? And there are a few variables to that. More filters, see through the noise, see less down the cable. That's a very good rule of thumb to use. And monitoring, 24/7 of monitoring is very useful for critical circuits, even if the circuits are new. As we saw earlier, there was a 5-year-old cable where they'd already experienced 2 faults. We tested and found another 2 PD sources that would have eventually turned into faults, and they were able to swap those joints out. So old, medium, or new, if cable circuits are critical, it's a very good idea to keep an eye on them. So to sum it all up, PD testing and monitoring of cables is going to improve your asset performance, which will give you a greater reliability and a safety aspect to your network, which over time will lower costs, and that will give you smarter investment decisions. It'll help prioritize where you spend your money, when you spend your money, and help you with decision making of managing your high voltage network. Here are our contact details, and we can be contacted via either of those methods there, emails or phone. And Neil's.
Any other questions, basically?
Yeah, and if you have any other questions, please send them through now. We've answered a fair few questions already within the question box. I believe that they would have got sent back to, did you guys send to all?
Yep.
Yeah.
Can PD only be determined that, oh no, we've answered that. You've done that.
Answered that one.
I think we're not sure we have answered.
Yeah, so most of them just chat.
Yeah.
Oh, there we go. So we've just got a question come through.
So yeah, Mohammed. Does the quality of the sheath screen have a big impact on the accuracy of results, and does bonding arrangement play a part of it? Yes, to a certain extent. The main thing when you're testing, so the HFCT has to be around you need to get all the signals basically. You can't have multiple paths to it. So from that cable sheath, you have to have that HFCT around, which is why when we're talking about the paper lead cables, if you've got a plumb joint in there and that's not got an insulated lug, then you've got multiple parallel paths. So the signals will go on the cable earth as well as the earth around the lug. So you're going to lose most of the signals there. So the main thing is that you need to go on all of that. It is technically possible to go around the conductor itself once the earth sheath is taken off. That can give you cleaner signals, but you run into issues with loading, saturation of the RFCTs and things like that. So a decent earth. The other thing is a safety aspect. We have come across situations where people were earthing down with very small earths, which is inadequate to take a fault current, basically. So that's the safety aspect. So we've had people installing HFCTs onto inadequate earths, and when a fault current happened, that can basically blow the HFCT up. So it has to be a decent size, and you have to get all around the whole thing.
Yeah, definitely. And then bonding arrangements. Yeah.
Sorry, I didn't get that. Bonding arrangements. Right.
Yeah.
How widely is the PD testing used for commissioning activities? Especially after a cable joint has been. It should be important. How wide is it used is possibly not as widely as it should be. So if we look at that industrial site where we've got 2 parallel feeders, 4 commutator feeders, and we've had 2 failures within 5 years, and 2 significant other discharges that were obviously there, they've probably been there from almost day one. We did find in that INEOS case study that maybe the immediate testing is not the time, but within a week the discharges sort of came up there. So I think it's not widely used. It probably should be more widely used. If you are going to do VLF type testing, so stress or high pot testing of cables when you're commissioning, then we would always strongly recommend that a proper PD test is done rather than just a withstand test. Withstand test is not realistically going to find you any underlying defects in quality workmanship of joints and things like that. So I think that first year or so of its life it's important. So if you're only going to do handheld out, my personal recommendation is always very much soon after energization test, and then 6 months, and then 12 months, and then maybe go to a 12-month period. And that's for switchgear and cables, because that's a critical time, and infant mortality is a thing, as we've seen. And also, if it's switchgear or cable joints, you might actually be under warranty for 12 months. So always worth finding the problems first.
Yeah.
Online PD useful for high TD cable. Not 100% sure what that means.
10 delta.
Oh yeah, high 10. Yeah, do you want to answer that?
Yeah, we've just had a question. Oh, we had one there. Oh, we'll just go with this one. Online PD is online PD useful for high 10 delta cable? So in the 10 delta, when you do the 10 delta test, there's a section in there in the standard that says if you get some high level 10 delta, that it can be attributed to PD, because what your 10 delta is doing is basically measuring the phase angle between your leakage current and your volts that are applied. So if you do have some leakage through that PD, so if when PD is occurring, sparks are occurring, and it will take some amount of current to run those sparks. And so if you do a 10 delta test and you get a poor 10 delta result, it could be an indication of PD. It's a hard one to say that it is, but it could be.
They will be detecting potentially different things. So just because you got high 10 delta doesn't necessarily mean you got PD. And if you've got high PD, generally that's not a massive indication of high 10 delta. So they're complementary techniques more than direct comparative techniques.
Yeah.
Okay. What's cable XLP insulation aging? PD always appears in aged insulation. Termination.
What's cable XLP?
Oh, right. So PD doesn't. I mean, I would say with XLP and aging and things such as, I don't know, water treating turning into electrical trees, that's not realistically what the PD technology is looking to find. What we're on XLP cables, the aging of the XLP, we're not realistically going to find, when PD happens on the XLP, it fails very, very quickly. So you generally don't get the opportunity to find PD, to monitor it, to trend it, other than out in the terminations or the accessories, the joints on the XLP termination. So we don't typically really look for, we wouldn't suggest a monitor on a cable where it's a short run of XLP cable and you've got two terminations and no joints in the middle. Really, we would only suggest to look at the terminations, because monitoring on the short run of cable, we have to find the PD very, very quickly. So permanent monitor is possibly better than, or always better than a periodic test, but we're not 100% sure whether you will ever have enough time to find the PD that is starting to occur and to do something about it before it fails. So on an XLP, we're really looking at the aging of the joints and the accessories and the monitoring of the joints and accessories.
Anything else? Yeah, no, that's pretty much it. And then we have one here.
Oh, how much noise, in your opinion, is attributed to both LV and HV VSDs?
Yeah, so if you have a lot of noise on your HV cables, it can be coming from anywhere. It really depends on where the section of cable is that you're testing and what is around that. So electrically around that. So as an example, I was at a solar farm not too long ago, and I was testing for PD on cables, and what we had to do was turn off all the low voltage inverters to be able to see the PD, and I could see them as clear as day because the solar farm was out in the middle of nowhere. It was in a paddock. There were no industrial sites nearby or shopping centres or anything like that that was putting noise back onto the earth screens of these cables. So we shut down the inverters. I could see the PD as clear as day. I could get a distance to it. I didn't need to apply any filtering at all. But then we did another test where we turned all the inverters back on, and I still knew there was PD there, but I couldn't see it because of the amount of noise that had been imposed through that. So yeah, low voltage and high voltage VSDs.
VSDs are a known source of interference. They are a known source of interference even when we're testing. So say we're testing on underground coal mines where they got VSDs, you find it affects your results. So if you can temporarily turn them off, that helps. I mean, when it's low voltage, low power, it doesn't always transfer that much. And that's why we always say that you need to assess the noise. So when Brad's talking about the solar farm there with those inverters, what we came across there is to find relatively low levels of discharge in the within that noise is actually a difficult thing. So in certain situations, the amount of interference and signals you get that can be coming from VSDs and low voltage can cause you a problem. So before we install a monitor, we tend to do an assessment using the more portable equipment to determine what sort of frequencies we need and whether filtering is appropriate. So you saw the first time when I showed the industrial plants where we could see the discharge 750 meters with a 1.8 megahertz filter, but absolutely swamped with noise from the processing plant when we were looking at any filtering below that.
To figure out, I've recently tested a few switchboards where there's been VSDs nearby. I didn't run any cable tests on those at that plant because I couldn't get to the screens of the cables. So the job was to test the switchgear, but I could tell that the VSDs were creating a lot of noise. So they create ultrasonic noise and they create TEV noise. And when you've got TEV noise, that's electromagnetic signals that I would expect if I put the HFCTs on the screens of those cables near that VSD, that it would be very noisy. And then we shut down one of the VSDs to prove that the noise was coming from there, and it was. So they do pump out noise.
Okay, next question. Comparing the direct positive PD pulse, some indirect PD pulses are negative on the online PDM. What's the reason?
I think it's what half the sine wave of the discharge.
Well, sometimes you do get that reflex. It sort of bounces when it sees an impedance as well. So it can be some indirect. What you may find when you're measuring, so you got the HFCT around, say, conductor, the red phase conductor. What typically happens if you're monitoring on the blue and the white phase or blue and yellow phase, depending where you are, you will see that in the opposite polarity. Some of that can be cross-coupling from the adjacent circuits coming back onto the original circuit as well. So you do see a small amount generally of these signals are flipped, but the majority of them will be in a unipolar one direction. But you will see a bit of that. The more filtering you put in there, sometimes the more that you see that sort of thing as well. But generally they're going to be in one direction. If you see something which is very bipolar, then that's usually an indication of something other than cable PD. But that's really. And the next question: was the Astute system used as a portable solution when performing the offline VLF? No. So technically difficult because of the amount of energization. So the two separate systems. The Astute system was used just a working voltage. Working voltage? What am I talking about?
Working frequency. Yeah. The monitor's designed to capture signals at 50 hertz, whereas your VLF's running at 0.1 hertz. So you may only get 1 or 2 pulses, whereas in normal situations you'd be getting thousands of pulses.
Okay.
Over the same time.
I think we're coming to the end of the questions. So we've got one. Thank you. Thank you.
Thanks, Stanley.
What's the next one?
Oh, yeah. Thanks, Tony.
Okay.
Yeah.
Well, we've come to the end of the allocated time. So thanks very much. We've got one more. Quick one right at the end. For 3 core HV cable, will online PD monitor be different by HFCT? For the 3-core cable, we saw one picture of a HFCT on a 3-core cable. You're realistic that, well, you're going to be measuring the PD signals, but what you won't be able to obviously determine is if it's phase-to-phase discharge between two of the phase. If you got a single screen, so they're separately screened, you won't see that. You're not going to be determining that, but you're going to still be able to see magnitude of discharge and discharge to location. At the end of the day, you're not going to really, the end result is if you got significant discharge in a location, whether it's a cable or the joint, and you're going to need to dig that out, the solution is exactly the same, whether you know exactly which phases are involved in that. So it's similar. Depends. The slight difference is whether it's belted cable or screened cable, but ultimately
Still possible.
Still possible. Yeah. Okay,
And that's it.
any further questions, or we'll bring it to a close, Brad?
All right. Thanks, everybody. Thanks for
very
joining
much.
in, and we'll see you on the next one.
Stay safe.
No worries.